All right, ladies and gentlemen, we are in the first day of Mathy Math here in Pre-Calc Honors, and we're starting with functions. Look at that. I even had a little fun there and capitalized the FUN. I'm sure you've never seen that one before. Anyways, today, guys, we're going to be going over some domain, range, and operations with functions. Those will be the main focus, but a lot of different stuff. Pretty much all review from algebra to honors, but I think we could use a little jog of our memory. All right, so let's let x and y be two non-empty sets, just meaning they have stuff in them, right? Now, a function from x into y is going to be a relation that associates with each element of x exactly one element of y, okay? Exactly one. Okay. Wonderful. So a lot of times we like to put it in a couple different ways, right? Not so mathy math talk. For a function, no input has more than one output. Okay. So let's think about it this way. If I wouldn't have this x going to multiple y's over here, that would then not be a function, right? It would still be a relation, but it would not be a function because an input, your x, has more than one output. As you can see, though, multiple x's can go to one y, and we'll see that here with numbers in just a sec. All right. Now, the domain of a function would be the set of all your x values or all your inputs, x values, inputs. And then your range would be your y values, mainly when we're looking at our standard xy coordinate plane, or our normal, equations that we're working with, or our outputs. But sometimes you'll see them in tables with different things that maybe aren't your x and y's, or they're using different variables. But this would be in general, okay? So the question below will address the numbers here is, can an element in the range be repeated in a function? For example, can a function contain the points 2, 4, and 3, 4? Why or why not? All right, well, does each input have no more than one output? Well, 2 only outputs to 4. 3 happens to output to 4. That's kind of like what we have going on right up here, but without numbers, right? So it would work. The input has one output. It's not like 2 maps to 5, 6, and 7. It only maps to 4 from what we know. All right, so that would be our why or why not. Lovely. Let's keep it moving. Actually, I want to go over here. Cool. So we want to determine whether a relation represents a function. We got a couple different examples here. This one over here is kind of what I'm talking about, where we just have like a chart. We're not dealing with our x and y's like we usually would, right? So here, no high school diploma, 7.7% unemployment. A high school diploma, 5.9. Some college, 5.4. College, 3.4. So does the relation represent a function? Meaning, does each input have exactly one output? You don't want more than one output for an input, so that'd be yes. It does represent a function. Function. Cool. How about letter B over here? Does each input have one output? Well, I've got 2 mapping to 3, 4 mapping to 1, 3 to -2, and then we have 2 to -1. I see a situation here where 2 is mapping onto 2 different numbers. Nope. Now, another way of looking at this situation is graphically. What if I had an XY coordinate plane? I'm going to try just quickly graph these here. So I'm going to pause the video real quick. All right. So we have the 2 points that we have in question here are the 2, 3, and the 2, -1. Now, if you think back to maybe a test to see if the graph of a particular relation or a graph of an equation that we had passed the vertical line test, right? No, it cannot pass through that vertical line more than once. Well, if I were to draw a vertical line, if I drew them correctly, they would be both passing through that vertical line at the same time, so this is not going to be a function, okay? So it's another way of looking at that. Now, the other 2 problems here will follow suit. We've got no repeating x's here, so that's another way of looking at it. If you're looking at ordered pairs, no repeating x's, I'm not going to have, an x mapping onto two different numbers. So this one is a yes. All right, determine whether a relation represents a function. Now we're looking at these equations. All right, so let's see here. We got ourselves a nice little equation of a line. If we were to graph that, starting down at -3, and we're going to go use our little slope down 1/2. Equation of a line. Every x is going to map onto 1y, right? We're not going to have x going to multiple numbers there. Also, graphically, we can think of it as like it's going to pass that vertical line test. Anywhere I put a vertical line on this thing, it's only going through once. So this next one's a little bit funky looking, right? And sometimes that can be a red flag as to whether something's a function or not. Sometimes you know it when you see it. Algebraically, what we can do is we can solve this equation for y. So let's do it. It's a lovely practice. So I'm going to take, I'm going to subtract 1, so I'll have, and I'm going to flip-flop some things around. So I'm going to have 2y squared, because I like having y on the left. Then it's going to be x minus 1. Hopefully that wasn't too crazy for you guys here on day 1. I know. Crazy stuff. All right. Then we're going to divide by 2. So I'm going to have y squared equals x minus 1 over 2. And then I'm going to square root. So I'm going to have y equals, and don't forget this plus or minus when we square root both sides, x minus 1 over 2. So when I'm looking at this problem here, again, remember we're thinking, does an x value, can I get two different y values then, right? Does an x value give me two different y values and not just one y value? So if I were to say plug a number in, like, I'm going to choose 9, and I have good reason for it. All right, so if I were to plug in 9 for x and evaluate, I'd have 9 minus 1 over 2, right? So that's going to be 8 over 2, which is 4. So I'm going to get plus or minus the square root of 4, which is 2, if I did a little bit of math in my head, right? So I put in one x value of 9, but I got 2 for an output and -2 for an output. So this would not be a function, okay? This would not end up being a function. It's a relation, but it is not a function. In order to be a function, we'd have to restrict our domain, which we'll talk about a little bit later, all right? So we're just going to be doing a little bit of evaluating some operations with functions. Oh, it's going to be fantastic. Let's start with the first one. F of 3. What do we do there? We're just plugging in 3, right? You should be like, yeah, no big deal, brother. No big, oh my goodness. Sometimes the snapping into a shape for a circle is fantastic. Sometimes it's not. Now, when we are substituting in numbers, guys, remember, I like to throw them in parentheses. Just a nice little best practice there, especially when we start dealing with negative numbers that are being squared. Oh my goodness. All right. So here I've got, 3 squared is 9 times 3 is 27, but it's negative. So negative 27 plus 6, that's going to give me negative 21. Wonderful. I do apologize for the 2 different 2s. Oh, man, that's going to drive some people nuts. I am sorry. Sometimes it happens. All right. The next one, f of x plus f of 3. Well, f of x is just the negative. Actually, I'll go ahead and write the f of x plus f of. Why am I doing that? I don't know why I'm being redundant here. That is ridiculous. All right. The next one here is f of x plus f of 3. So, well, f of x is just negative 3x squared plus 2x, and we just evaluated f of 3, right? Wonderful. Minus 21. And that's what that one would be right there. Cool. All right. F of negative x. So I'm going to throw in negative x for all my x's. So if I have f of negative x, I would have negative 3, parentheses, negative x, squared on the outside, definitely important, 2 times negative x. Oops. All right. So let's see here. I'm going to have negative 3, but then when negative x squared, and negative x gets squared, it's like negative 1 is in the parentheses getting squared, which becomes positive, so it's just squared, and then minus 2x. So that one does change sign. All right. How about negative f of x? What does that mean? That means I'm throwing a negative out in front of the entire function. So I would have a negative and then parentheses in front of everything, negative 3x squared plus 2x. All right, so I'm going to have, that's going to be a positive 3x squared, and then minus 2x. Excellent. This is good stuff. Don't forget to distribute that negative, especially when we get to like addition, subtraction. That's when you're going to want to distribute that negative. All right, f of x plus 3. This is, you guys are going to love this one because it's probably the biggest pain. All right, I'm going to have negative 3, and then in parentheses, substitute in that x plus 3, square it, and then plus 2, and then again in parentheses, x plus 3. Well, the 2 times x plus 3 isn't that bad. It's just distributing that. But I'm going to do a little bit of foiling first. Love me some foiling. If you just distribute this squared to the x and the 3 and call it x squared plus 9, I'm going to be very upset. And right now remotely, but hopefully in the future we're back in person and you're still watching this video maybe for fun. But I'll be very upset. All right, we got to foil it. You got to think about that as x plus 3 times x plus 3. So I get x squared plus 6x plus 9. If you need to, write it out as x plus 3 times x plus 3. And then we have plus 2x plus 6. I'm going to distribute that negative 3 now. Negative 3x squared minus 18x minus 27. And then we're going to be able to combine some like terms. I love combining some like terms. It's just a fantastic way to organize using math. You know, so minus 16x. Then negative 27 plus 6 is going to be negative 21. Lovely. Good stuff. Any questions? No? Okay. Wonderful. Let's keep it moving. Keep it moving. So this next one, we're going to be talking about implicit versus explicit form. So when a function f is defined by an equation x and y, we say that f is given implicitly. Implicitly. That's fun. All right. If it is possible to solve that equation for y in terms of x, like your normal looking equation that's easy to throw into your TI-84 plus calculator, you know, it's easier to work with. Then we write y equals f of x and say that the function is given explicitly. All right. So we want to circle the functions below that are written in their implicit form. All right. So this one will be in the implicit form. All right. It could be written explicitly, but it currently is in its implicit form. The next one here, that's going to be explicit, but this one is once again going to be in the implicit form. All right. With a little bit of maneuvering, just subtracting 3x over, now it's explicit. Right? Cool. Wonderful. Fantastic. I mean, you can maneuver this one over here too. You can divide by x. Boom. America. Awesome. Cool. All right, let's talk some domain here. All right, we're using some equations here of various functions. So let's look at letter A here. Find the domain of each of the following functions using interval or sepal notation. We're going to use some interval notation here. I believe in your online book, they want you to use interval notation as well. That's with the parentheses and the brackets and the union and the intersection. Yes. Fantastic. It works well a lot, but sometimes it... All righty. First one here. Let's think about... first off, we start with all real numbers, right? Yay! Everything's in this graph. But now we need to look at, well, what can't exist here? What's a no-no in this particular function? We're talking about A here. We have a fraction, right? We have a quotient here. So what am I not allowed to do when I'm dividing? I cannot divide by 0. So how about we find out when that denominator is 0? How do I do that? Oh, I'm going to factor. All right, we're going to set x squared minus 2x minus 3 equal to 0. And we're going to factor, hopefully. Otherwise, we'll have to use the quadratic formula. I want to find out when this is 0 so I can say, hey, it's good except for these particular numbers, right? So what multiplies to negative 3 and adds to negative 2? Well, that'd be x minus 3 and x plus 1. If you don't remember how to factor, we got to practice that. All right, so I'm going to get x equals 3 for this one and x equals negative 1. Wonderful. I set each factor equal to 0, right? Did a little bit of algebra in my head. Cool. So when I'm writing this out, I'm going to start with negative infinity. I'm going to go to -1, not include it, pick it back up with -1, not including it, right? We don't want that in our domain. Then go to 3, union again, almost forgot my union, and then 3 to infinity. Okay, so that would be our interval notation. For set notation, you'll see it written in different ways, like brackets, x such that x equals all real numbers, except x cannot equal 1 or -1 and 3. Okay, so, and there's shortcuts of writing those things, but that's the set builder notation. When you're entering it online, it uses interval notation. So got to be savvy with both, if you will. All right, the next one. I have a parabola, right? So my domain, well, let's think about a graph of a parabola, or really, is there any number that I can't throw in for x if I'm talking about the domain of that function? Can I not square any particular numbers? No. So this one's going to be all real numbers, or -infinity to +infinity, or if you're doing the set builder notation, all real numbers. Whoa, I messed up my teacher brackets. How did I do that? It's because I didn't do this one first. All right, cool. Either one of those, cool. But again, this is what your online book will want. All righty, the last one. It's a radical, right? Square root. It's radical. It's rad, brah. So what are we not allowed to do in radicals? Because there are some no-nos there. I cannot square root what? Some of you might be thinking 0. 0 is cool to square root, by the way. It's negative numbers, okay? So I want to make sure that this is greater than or equal to 0. So we can either find out when it equals 0 or set it greater than or equal to 0. It's up to you guys. So let's see here. I'm going to say 3 minus 2x equals 0, and I'm going to solve for x. So I'm going to subtract 3. I'm going to have -2x equals -3. So x is going to equal 3 over 2, okay, or 1.5. So what does this mean? Let's think about the behavior of this. I like to often set them equal to, because I'm finding more like these critical points, and that will come into play in other lessons in the future. Okay, so I like to find out where my critical values are, where it's going to be 0, where it's going to be negative, things like that. And when it's 0, you're changing sign. Okay, so if a number is larger than 3 over 2, then you'd end up with, let's see, if it's 3 over 2, you're going to get 3 minus 3 is 0. If it was 4 over 2, which is larger, then you're going to get a negative number. That's no good. So we actually want to be less than this, or any number from -infinity to 3 over 2 is okay. All right? And actually, including that, right? Because we can square root 0. Almost made a little mistake there. All right, that would be my domain for that one. And you could also write that as x such that x is less than or equal to 3 over 2. But again, the book is going to want in interval notation, which is the first one, which is why I'm circling that one. Okay? So again, I did a little sign check. I said, hey, plug in some numbers. If I go above that or below that, what's happening? Am I getting negative? Am I getting positive? That'll tell me. Woo! Application. My favorite. All right. Find the domain of an application problem. Now, application, we got to think a little bit differently here sometimes. So, and we'll explain what I mean by that in just a sec. We have a rectangular garden that's a perimeter of 100 feet. Express the area of the garden as a function of width and find the domain. Okay. How about we draw a picture here? I, too, have a rectangular garden. I got some watermelons going right now. I got some peppers. Woo, it's awesome. Bunch of tomatoes, actually. They're like way taller than me, which I guess isn't saying much because I'm pretty short. But I mean, some of them are like 7 feet tall. It's insane. It must be the river water that I'm watering them with. Okay, so my perimeter is 100. Well, let's say my width is, I'll make this my width. And if it's a rectangle, the opposite sides are congruent, right? Now, my length, I don't want to introduce another variable here, but what if I were to say this? If I had my perimeter was 100 and I were to subtract 2 widths, that's what I'm left over in like the perimeter of the garden or the fencing I could use for the garden, right? And I want to divide that equally into both sides here and here. So if I were to divide this by 2, that's my length. Everything's divisible by 2, so I can make it 50 minus W and 50 minus W. Okay? Awesome. Wonderful. Now, what is my area of this garden? And one thing I want to point out to you guys is if I added all these sides up to get the perimeter, the W's would cancel and I'd be left with 100. Hey, that makes some sense, all right? Now, my area as a function of width is equal to length times, or width times my length, or length times my width. I wrote it like this because it looks a little nicer. I feel like when you put the, the W out front of the parentheses, otherwise it looks backwards. All right. So let's look at this here. What's my domain, right? So in this case, normally, like if this was just a normal function, we could have anything we want. This is just a quadratic function when you distribute that W. And as we saw before, our domain of the quadratic function was all real numbers. But can we really have all real numbers in the context of this problem? All right. Could I have a width of 0? No, that would not make sense. That wouldn't be a rectangle, right? Could I have a width of over 50? Well, if I have a width of 50, or actually 50 or more, now my length is going to be negative, right? Or 0. That doesn't make sense. So I guess what we're getting at here is that it's going to have to be between 0 and 50 for my domain. Okay? Because if it's 0, then I'm going to have an area of 0. I'm going to have a width of 0. That doesn't make sense. I have to have some dimension. If it's 50, then it makes my length 0. So same concept. There we go. Bippity bop. Just don't stop. Love some application. Can't wait to do more. All right, I'm just going to do a couple of these guys because I know this video is getting long here, and I think most of them will be able to practice on your homework. You just need a little refresher. So for part B, I'm gonna jump right to B here. It says f minus g of x, right? Or f of x minus g of x. That's another way of writing this, is f of x minus g of x. So let's write that out. That would be 2x minus 4 minus, and I'm going to toss some parentheses there because we got to remember to distribute that negative, right? That goes to both of these here, okay? Now, I'm just going to scribble this out and keep moving our way down. We won't do that one. So I'm going to have 2x minus 4 plus 3x minus 6, and now what I get is 5x minus 10. Cool. All right. I'm in battery saver mode. Oh, I better finish this up. All righty. The next one I want to do, or at least talk about here, guys, we're just multiplying the two. You're going to have to FOIL, right? Let's jump down to, how about, let's go with G. All right, now if I want to do this one, I'm going to go with a different color here because I've been using red the whole time. If I want to do this one here, there's a couple ways. I could multiply them out first and then plug in the -1, or I could evaluate first. I often find that it's easier to evaluate, so I'm going to do 2 times -1 minus 4 times, and then we have -3 times -1 plus 6. Now, it looks a little bit messy, but I'm going to clean this up real quick. This is -2 minus 4 is -6. And then this is going to be +3 plus 6 is 9. And I'm going to have -54 as my answer. Awesome. So otherwise we would have had to have FOILed that out, and oof, it gets kind of messy. Well, not really. It's not that bad. It's foiling. But plugging it in, working with the numbers, it was much easier, I think. Alrighty. The last one I want to do is D, part D up here, and that one is probably the most important. All right. So for this one, we got a couple things we got to worry about. Because at first it seems pretty simple. All I'm going to have is my f of x, which is 2x minus 4, over my g of x, -3x plus 6. Now, can I do any simplifications? There's no greatest common factor that I can take out of both of them that would cancel. This one has a -3. This one has a 2. That's not going to do anything. I can't simplify this at all. So I'm done. almost. I also have to have my domain, right? Which we could say where, and we could either use set or interval notation. We'll do interval for now. What is x not allowed to equal? What can I not divide by? I can't divide by 0. So I got to solve that denominator for 0. Let's do a little side work here, and I'll do that in purple. Negative 3x plus 6 is equal to 0. So I'm going to have negative 3x equals negative 6, and I'm going to have x is equal to positive 2. So it can't equal 2, otherwise I'll be dividing by 0. Some of you might have just seen that and done the math right away. I like to show some work sometimes. All righty. So what I'm going to have here, from negative infinity to positive 2, union 2 to positive infinity. Or you could see it where they say where x does not equal 2. And when we're excluding numbers, that's definitely the easier way of writing things, you know. But computer program works one way, I guess. All right, you know what? On second thought, I think that's probably enough here for this first video. We gotten pretty into it here. So again, showing you a couple different ways to write domain, a couple different ways to write range in the same way, right? It just kind of, if you're using the computer program, sometimes certain books write it different ways. It's good to be well-versed in that way, all right? So I hope you guys enjoyed this first one. I know I certainly did. You guys have a great day. America, freedom, rock and roll, Costco, and Riverdog Jenny. If you don't follow Riverdog Jenny on the gram yet, I would suggest popping on there and following Riverdog Jenny. All right, that is my dog, yes, if you don't know that. All right, have a wonderful day, guys. Peace.